Hey everybody. So for today, we're taking a look at lesson number 6, factored form of a quadratic. We've already learned how to write an equation in standard form. We've taken a look at vertex form earlier this week. And now this is our third way that we can write quadratic equations. Our goals for today are to identify the x-intercepts, also called roots, of a quadratic function in factored form, and also to be able to write a quadratic equation in factored form when given the roots. After you're done watching the video and answering some questions today, I would ask that you complete the day 6A assignment in Schoology. I believe it's just 4 or 5 quick questions to check for understanding. All right, so factored form. Here's what it looks like. We have y equals a times x minus r1, or r sub 1, in the first parentheses, and then in the second parentheses, x minus r sub 2. Now the r1 and r2 that you see here in the equation are just representing the roots. R stands for root, and the little 1s and 2s are just because there's 2 different roots. R1 is the first one, R2 is the second one listed. And those roots again occur at the x-intercepts of the graph. So when we look at our graph, we're thinking, what are the roots of this function? Well, we know that roots occur at the x-intercepts. So all I have to do is find my x-axis and the points where our curve, our parabola, cross the x-axis. Those are the x-intercepts. So we have one of our roots. I'll go left to right, and we'll call this r1 is at -5. And r2, our second root, is at +3. So those are the 2 roots of this particular function. Since x-intercepts occur on the x-axis, they will always take the form r whatever, whether it's r1 or r2, comma 0. Because anything that falls on the x-axis has a y-coordinate of 0. So the second number is always going to be 0. So in an equation below, these are actually linear equations. But what we can do is identify the x-intercepts, or the roots, by letting y equal 0. So what we're going to do is replace the y with 0 and solve for x. So I want to add 8 on each side, and I get 8 equals x. In other words, x equals 8. Okay, so one of my roots occurs at 8, comma 0. For number 2, we can do the same thing. Let y equal 0 and solve the equation for x. This time I want to undo addition, so I'm subtracting. And I get -5 equals x. So my other root occurs at -5, comma 0. So to find the x-intercept, or the root of the function, let y equal 0, solve for x. And then we can write our solution as an ordered pair. This time we are working with quadratic functions, but the concept is still the same. To find the x-intercept, or the roots, we let y equal 0. So I'm going to replace the y with 0. And this time, in order to solve for x, we have to be familiar with what's called the zero product property. Think about it. If I want to multiply 2 numbers and I get a product of 0, how is that possible? It's either that the first number has to be 0, so 0 times something, that equals 0, or it's got to be that the second number has a value of 0. A times 0 is equal to 0. So if I multiply any 2 positive numbers together, I'm going to get a positive answer. If I multiply negative numbers together, I get a positive answer also. If I multiply a positive times a negative, I'm going to get a negative answer. But the only way that I can multiply 2 numbers and get a product of 0 is if one of those 2 numbers happens to be 0. So let's use that to our advantage. In this example number 3, here's that first factor. X minus 4 is a factor. So how might x minus 4 equal 0? Well, it will equal 0 when x has a value of 4. In other words, 4 comma 0 is an x-intercept. What about the other factor? My other factor was x plus 1. Well, how might that equal 0? Well, I solve for x. I see that x equals negative 1. So negative 1 comma 0 is the other x-intercept. So my roots occur at 4 and negative 1 for that quadratic function. Let's take a look at number 4. If I let x equal 0, if I let y equal 0, my equation looks like this. So I'm going to take each factor, so 2x plus 3, set it equal to 0. I'm going to take the other factor, x minus 6, and set it equal to 0. Because one of those two factors has to equal 0 if they multiply together to have a product of 0. So let's solve. Ooh, a little bit more work to solve this time. I start by subtracting 3, gives me 2x equals negative 3. Now I can divide by 2, gives me x equals, well, negative 3 halves, or negative 1.5 if you want to divide it out as a decimal. So I have an x-intercept at negative 1.5 comma 0. When I solve the other one, it's a little more straightforward. I just add 6 on both sides, and x equals positive 6. 6 comma 0 is another solution, my x-intercept. So my roots this time are at negative 1.5 and positive 6. So let's take this the other direction. Can I start with the roots, or the x-intercepts, and write the equation of the graph? Slide this over. I can see on my graph I have a root at negative 5. I also have another root at 3. So I want to think of that as my R1 and my R2. Root number 1, root number 2. Do you remember the form of the equation we wrote earlier in our notes? Y equals A times x minus R1 times x minus R2. Now A can be any number. However, I notice my parabola opens up, so it really should be a positive number. It can just be 1, or it can be 2, or 3, or 4, or 5, or even 1/2, or 2/3, or 4/5, but it needs to be a positive number. Okay, so you can pick whatever you want. I'm just going to pick a 2 for now, just randomly. It's a positive 2. I have x minus my first root. Well, my first root was over here at negative 5. So x minus negative 5. My other root was R2, and that was a value of positive 3. So x minus 3. Now it looks like I need to clean that up a little bit because I have double signs. My x minus negative 5 becomes x plus 5. And x minus 3 stays the same. So that's one possible equation that might work for that graph, at least for the roots of negative 5 and 3. What's another possible equation? Well, anything as long as my leading coefficient is positive and my roots show that they're negative 5 and positive 3. So basically x plus 5 and x minus 3. Could be 3 in that position. It could be a 1/2 as a leading coefficient. It could be 14 for all I know. But what it can't be is it can't be negative. Okay, that's the one thing it can't be. Because our parabola opens up, I know it cannot be a negative number. All right, let's look at one more. Let's write an equation in factored form if the quadratic function has the roots 7 and negative 3. Well, it's basically the same thing we just did, except we don't have the graph, but that's okay. If it has the roots of 7 and negative 3, I know that the x-intercepts are like 7 comma 0 and negative 3 comma 0. So I know my R1 can be written as a 7. My R2 can be written as negative 3. And I can write my equation using that format from before. So y equals a times x minus the first root times x minus the second root. And let's just sub in what we know. Okay, so x minus the first root, which was 7, times x minus the second root, which was -3. And you remember what happened on that last one? Instead of writing it as x minus -3, I'm going to end up simplifying that. So I'm just going to do that now and write it as x plus 3. The big question is, what number can go up front? Well, it doesn't say anything here about if it opens up or opens down. It doesn't tell us what to use for the value of a. So I guess we could put any number there that we want. We could leave it blank, which would indicate that it's a 1. I could put a negative sign there, which would indicate it's a -1. I could put any other number there, like a 2 or a 3 or a 4, because it doesn't say specifically what it can or cannot be. So technically, this is an equation in factored form that has the roots 7 and -3.